Hi, and thanks for joining this Telit Cinterion webinar, The Advantages and Challenges of Migrating from 4G to 5G. I'm Amanda Flink, the Head of Global Events here at Telit Cinterion, and I will be moderating our event today. To explain this topic, I'm pleased to be joined by Marco Contento, the VP of Product Management, Mobile Broadband at Telit Cinterion. Now, just before I hand it over to Marco to start our presentation today, I do have just a few quick notes for our audience. I would like to remind you that we have time to answer some questions at the end of the presentation. You can simply submit a question by posting in the questions box located near the bottom of your screen. Also, please be sure to check out the resources section for some additional information on today's topic. And finally, we will send out this replay link to all attendees at the conclusion of the webinar. And with that, Marco, I will hand it over to you to start our presentation today.
Thank you, Amanda, and welcome to the audience. So we'll start talking about this important topic and related to the migration from 4G to 5G. So let's start with some background before getting to the main topic of the webinar. The aim and vision also the 5G is to develop one network capable to support multiple and widely different use cases, such as mobile broadband, massive machine-type communication, and ultra-reliable low-latency communication. To serve the mobile broadband use case, 5G requires support the higher bandwidth. Thus, additional frequency have been introduced in the sub-6 spectrum and also in the millimeter wave spectrum. 5G has been tested operating at the 5 to 8 gigabit per second with 5G NR, and in millimeter wave can provide potentially more than 10 gigabit per second. Instead, to serve the ULC use cases, 5G has been designed to offer much lower latencies that we have ever had in the cellular domain and with the legacy technology. Ultra-low latency is required with the mission-critical real-time response is required. The third pillar is represented by the massive machine-type communication. 5G services are better equipped to handle these varying traffic types and connected devices. It's also designed to be scalable and provide efficient connectivity of a large number of devices sending short packets. All three milestones are being also represented by the three major 3GPP milestones in regard to 5G standardization, like Release 15, Release 16, and now Release 17. We have some example of those use cases. For instance, we talk often about smart logistics. Logistic field, including transportation, has been expanding its use of IoT to monitor shipment, either in a home country or over international border and around the world. The industry is also moving forward with its use of autonomous vehicle in warehouse operation and on the road. Manufacturing operation is another important use case. 5G also a lot of promise for the manufacturing sector, promising more flexibility than the legacy wired networks such as industrial Ethernet, while retaining the high capacity, high reliability, and low latency manufacturing needs. 5G supports the ability to reconfigure automatic manufacturing operations so they can more quickly meet changing market needs. So we can continue to list additional use cases that somehow can be let's say linked to the three main pillars of the 5G vision. These use cases, however, require to use low bands, mid bands, and high bands. In particular, low bands to provide coverage inside the metro areas and inside the building. Mid bands for capacity, and in particular, in between frequency in the range of 2.5, 3.5 gigahertz, and high bands for extended capacity in hotspot. This kind of area. Low-band spectrum usually are used for nationwide coverage with huge geographic areas requiring rapid 5G services. Transmitting on the 600 MHz frequency, for instance, that was used in the past for TV broadcast, one low-band tower can serve customers within hundreds of square kilometers, enabling coverage even in a rural area. Mid-bands like 5G today is likely to become available in all the major metro areas and across every major carrier. This flavor of 5G may constitute the minimum 5G performance in some countries. Some carriers will skip low bands or 5G altogether. Carriers are able to allocate larger chunks of transmitting spectrum to mid-band 5G than low-band 5G, as data speeds are markedly higher. Within the cellular industry, it's clear to everyone at this point that mid-band 5G is the sweet spot for 5G distance and performances, assuming you live within a couple of kilometers from the tower. What's the issue of 5G? Well, most of 5G network use only mid and high bands, and therefore 5G services struggle to reach urban center and go deep inside the building without the use of low band. We'll see later what are the typical deployments that the network operator has implemented so far, and in particular in the early days. Today, the introduction of frequency bands in infrared spectrum in many markets involve the 3.5 GHz spectrum, also known as C-band, although there are deployments using low band, such as in 700 spectrum, 700 GHz, 700 MHz spectrum. Some operators have been able to close the legacy bands and refarm frequency to LTE, but many others have kept 2G and 3G running to maintain the legacy devices and provide also the circuit switch voice support. As a result, many operators do not have availability to deploy 5G on those bands. Refarming 4G into 5G NR is not always an option, because most of the traffic will continue to run on 4G for the next years. DSS, dynamic spectrum sharing, addressed these challenges by allowing the operator to run 5G on the existing 4G bands without the need of refarming carriers and with a minimum impact on the service. Dynamic spectrum sharing allows LTE and 5G to coexist in the same carrier using spectrum sharing. The time frequency resources in the carrier are dynamically assigned to either LTE or NR according to their respective traffic demand. From the operator perspective, the clear benefit is DSS is that they can build nationwide 5G cover without the need of permanently refarming LTE spectrum or buy new frequency bands in 5G on low bands. They can adapt to traffic demand and roll out DSS fairly easy. DSS is possible through software upgrade in the majority of the cases on the existing base station hardware, which is not cheaper but also quicker than other methods. The main challenge is the increase of scheduling complexity because DSS will require rapid coordination between the LTE and the NR part. In the early 5G NR market, DSS is an advantage in that it allocates only the required amount of time frequency resources for the few NR users and reserves the remaining resources for the LTE services. Over time, as the number of NR users increases, DSS accordingly allocates the required resources for NR purposes. In turn, this flexibility spectrum sharing solution allows for a smooth 5G transition. Let's look at an example of a spectrum allocation for a 5G rollout that included DSS. If you look at the first 5G spectrum deployment, the operator is using, in this case, a 3.5 GHz spectrum for capacity. Another area is in the low spectrum bands, so around 700 MHz, for the coverage for wide areas and also to do carrier aggregation between the low band and also the bands in the 3.5 GHz. Everything in between is used either for 4G or also for 2G and 3G. The next step for the operator is the gradual introduction of dynamic spectrum sharing on LTE bands between 1.8 GHz and 2.6 GHz and eventually also in 900 MHz, depending on the strategy on 2G and 3G. 800 MHz in this case is stay in LTE to provide coverage and voice over LTE, but other than that, DSS will be deployed. What are the challenges of DSS? These are essentially the bad news of all the story. An inherent resource overhead exists in DSS operation. Although the dynamic switching is a key benefit in DSS, it does incur in operational inefficiency that reduces the total available capacity of the band. For instance, if the LTE and NR traffic are evenly distributed in the network, an operator may be able to achieve a larger capacity by equally dividing the spectrum into LTE and NR bands and evenly allocating LTE and NR users to their respective spectrum, rather than by operating DSS. If the spectrum is evenly divided, total capacity simply becomes the capacity that each system can achieve within its spectrum band. In the case of DSS spectrum, instead, due to the overhead caused by the DSS, the total amount of resource can be allocated to the two systems is reduced. When NR and LTE traffic are similar, the two systems will almost evenly divide the entire source, so that the capacity is reduced by the ratio of DSS overhead. Similarly, as the traffic demand of the network and the cell load increase, total cell capacity deteriorates as a result of DSS overhead. This deterioration not only degrades total cell capacity, but also directly reduces the peak data rate of the NR and the LT UE by affecting the transmission performance. When the frequency band is statically divided into NR and LT, instead, it's possible to achieve peak rate by aggregating the NR and LT carrier. But when using DSS, peak rates deterioration occurs. Let's see instead when another point, we look at using DSS on multiple bands that does not always achieve the expected benefit. The scenario on the left shows the amount of LTE and NR traffic that a base station can handle when operating both bands under DSS as NR demand gather increase. The scenario on the right shows the traffic when one band is operating as DSS and the other is referring from LTE to NR as the NR market reaches maturity. In both cases, when NR demand is relatively low, it is possible to allocate resources flexibly and efficiently. When both bands are operating as DSS, however, there is a greater overhead that hits into the available LTE resources and ultimately reduces the total available capacity. Over time, when traffic demand for NR gradually increases and exceeds the capacity offered by the DSS band, prefarming the LTE band as an NR band can satisfy the greater NR traffic. This can also increase the total capacity of the system compared to a multi-band DSS. We'll see later an example. Here we are. So, let's look at the test result. This is a test result provided by Keysight on a DSS implementation 5G NSA lab test network, where the test configuration consists in a network using the LTE-MB-SFN-based DSS method, 5G NSA as an LTE anchor on band 20, so in 800 MHz spectrum, LTE 5G share carrier in band 3, so 800 MHz spectrum, so both 5G and 3 and LTE band 3. Two devices connected, one supporting legacy LTE, so no compatibility with the 5G, and the other device, of course, 5G capable. Both devices were capable to support 2x2 MIMO, 256 QAM in both LTE and 5G in either RF condition. So 20 MHz LTE channel dynamically allocated between LTE and 5G. So without enabling DSS, the projected throughput achievable by the two technology and devices, I would say, are under 95 megabit per second in the LTE and 226 megabit per second for 5G. So here, we noticed 15% more throughput in 5G. If we enable DSS instead, the maximum throughput achievable in the system is 160 megabit per second with LTE and 5G combined. So if we calculate the DSS overhead, we can easily understand that we have a 21% overhead compared to LTE only. If we compare to the, let's say, LTE only configuration without DSS, of course. In the contrary, if we compare the DSS deployment with the full throughput I can achieve with 5G, I can get 41% of overhead. Again, no DSS. Of course, the result may differ depending on the network implementation or on the configuration of the specific implementation. Now, what's happening? Because the capacity and throughput reduction while implementing DSS, network operators are refarming more and more bands from 4G to 5G to launch 5G SA, so standalone, in higher carrier aggregation combination for 5G. This will result in the next year, starting already from 23 and 24, in limited spectrum left over for 4G, typically on low and mid bands to serve legacy LTE devices and for fallback of voice over LTE. So operator recommendations are essentially to focus on category 6 or category 12 as a technology requirement for LTE, pure LTE devices, stating that hereafter LTE devices still need to be served, but peak data rates are decreasing in importance. They will be launching higher and higher carrier aggregation combination for 5G, taking spectrum away from 4G. Now, a few words regarding the two different architectures, because we have mentioned DSS, but we didn't touch yet the difference in architecture between non-standalone and standalone. So starting from 2018 and 2019, mobile network operators have deployed and commercialized 5G NSA, so non-standalone network across the globe. Network operator could quickly get into high-speed 5G service by rescuing legacy 4G infrastructure by means of software upgrade. Signaling goes through over LTE core network, while the radio access resources are combined among 4G and 5G. This has allowed a gradual migration and, even more important, investment in the transition to 5G. However, to leverage the new and powerful features such as ultra-low latency communication, industrial IoT, and network slicing, simply to unlock the potential of 5G, mobile network operators have to migrate to 5G standalone architecture. This will, of course, require that the core network will be a pure 5G core network, and there will be not anymore the use of the 4G part. This transition will allow new 5G services to capitalize on new revenue stream and allow users to enjoy the full benefit. So, because these dynamic spectrum sharing challenges and the consequent spectrum refarming from 4G to 5G, there will be limited spectrum for devices like those in the category 18 or category 16, so able to combine multiple carrier LTE, such as 5CA, for instance. So, instead, lower spec LTE devices, such as category 6 or category 12, will be able to operate at their peak speed. In this scenario, Telit and Cinterion recommend to replace high-tier LTE devices such as Cat16 or Cat18 with 5G solution, and we refer to the FN980, FN990, FE990 LGA, and also the MV32. In the mid-tier segment, instead still represented by LTE, we offer an N920 in different categories, so category 6, 13, and 12. In the low-tier segment, equivalent to LTE Cat4, we have enrolled a 5G RedCap solution that will come late this year. So let's look at the product fit compared to the network operator roadmap. Back to the spectrum transition from carriers and how the product fit into their roadmap. You remember that in the early days of 5G deployment, so starting from, let's say, end of 2018, but in general 2019, operators were focused essentially in launching 5G NSA. So combining multiple LTE component carrier along with one component carrying 5G, typically on the high and ultra high bands. So the first generation of 5G devices were capable to combine one CC with multiple LTE CC. Of course, the game changer were the high bands, like those in 3.5 gigahertz, where there is a lot of spectrum available, and also the channel bandwidth that in TDD bands can be up to 100 megahertz of bandwidth. Among 21 and 22, carriers started to refarm or deploy DSS, so dynamic spectrum sharing, and thus either two-component carrier or three-component carrier are at this point required to be supported at the product level, and in particular in standalone mode. Standalone mode that is being gradually launched by the carrier worldwide with the aim on long terms to focus on 5G SA, so 5G standalone service, and to leverage, as said, the advantages we have seen so far. From, let's say, 2023 or 2024 and onwards, carrier will start to support four-component carrier aggregation and even more. So let's have a look at the portfolio of mobile broadband product at the Telit Cinterion, where we essentially cover all the needs across the technology, so starting from LTE category 6 up to the latest and most recent version of 5G for different use cases, either for public network and also for private networks. First product of the category of the portfolio is the LN920 family that is available as a single SKU for global deployments, capable to work on private but also on public network. Can be offered in different flavors in terms of throughput capability in downlink and in uplink. There is the option also to support in embedded SIM. We offer the support of security enhanced Linux as a state-of-the-art for the security part. It does support also GNSS with the L1 as the band support for the GPS GLONASS, Beidou, and Galileo. Typical applications of this product are fixed and mobile broadband, industrial gateways and enterprise user, mobile computing, rugged laptops and tablets, and also other devices such as video streaming devices. The other product family is the FA990. That is again a data card that is compliant to release 16 standard. Also, in this case, it comes as a global SKU, so able to work potentially on every network in the world. It has a dedicated GNSS antenna port with internal LNA, capable to support L1 band. It can support both PCI Express and USB by means of switching via GPIO. Can also deliver as with an embedded SIM already mounted. It supports a QMI interface and also an embedded processing by means of our own implementation, which is called Upzone. This product is available in 30 by 52 millimeter form factor, single side M.2, and also in extended temperature range. Next is the V32. This specific SKU fit the standard M.2 30 by 42 millimeters and is capable to support also in a specific product area also the millimeter wave spectrum. This specific SKU is designed for constraint size applications, in particular mobile computing, industrial gateways, whenever there is the need to have a standard M.2 form factor, for instance, similar to the LN920. So last born in the Telit portfolio, Telit Cinterion portfolio, is the FE990, which is based on the same platform that we have in the FA990 series, so the M.2. But in this case, we have decided to develop an LGA form factor in order to have an extensive hardware interface for maximum design flexibility. This is a product designed at particular fixed wireless access application, and I refer to CPE in particular, in order to have the flexibility to attach multiple peripherals. This device comes into an LGA form factor that is 41 by 41 millimeters and is available in two flavors, one for North America region and the other one for EMEA and Asia Pacific. It can support GNSS, both L1 and L5, and support also Upzone Linux, so the application development environment that is also available on other product lines. We support also OneS, that is the software suite that is designed to do device management. It comes also with all the security features such as Secure Boot, TLS, DDoS, and many others. Now, moving to the conclusion of the presentation, we have essentially, we went through the initial, let's say, analysis of 5G, and in particular the use cases that 5G is aimed to support. And we went also through the discussion regarding the spectrum needs, in particular the need to support bands from low spectrum up to high bands. And then the issue of the 5G and LTE coexistence, considering that today the network operator still required to support the legacy LTE devices, not to mention also 3G and 2G. And then the new technicality or method to support this coexistence by means DSS, so dynamic spectrum sharing. And we have also looked at what are the challenges of this capability, that in other words, reduce the capacity of the system, but also the peak throughput that can be achieved by the two technologies together. So we went through the spectrum transition, so that we are experienced today, looking at the network operator that gradually are refarming the 4G spectrum into 5G spectrum, either NSA or also standalone. And therefore, the future trends that are essentially our guidelines we have to look at when we decide or when we need to develop a new product. Last, we went also through the Telit Cinterion portfolio, in particular for broadband products, that helped customers to transition from 4G to 5G. Thank you for listening me, and now Amanda you can take the stage.
Perfect. Thanks, Marco. And just before we get to the questions, I am going to drop a poll on the screen here. If you'd like to have one of our experts contact you directly, please just respond here on the poll and we will have someone reach out to you. We do have time for a few questions, like Marco said, and we've gotten a couple so far, so we'll do our best to cover those in the time that we've got left here. Marco, the first question we received: how is the extended capacity achieved in high bands in 3.5 gigahertz spectrum, and how is this spectrum used by the carriers?
Well, the benefit of this part of spectrum that is in ultra high band is that the total bandwidth available is very wide, and therefore they can accommodate, of course, many users, and therefore the capacity of the system increase. And therefore the carriers have started to deploy in this spectrum along with the low bands, and by mean doing carrier aggregation between these very high band or ultra high bands along with the low bands. The advantage is that in this spectrum, the maximum bandwidth for each channel is up to 100 megahertz spectrum, so quite a lot, and therefore they can achieve multi-gigabit throughput. In the contrary, in the FDD bands, usually the channel bandwidth is in the range of 20 megahertz, sometimes something more, but no more than 30 or 40 megahertz.
Great, thanks. Next question: what is the difference between DSS and 5G standalone?
Well, DSS is a method, let's say, that allows the network operator to deploy or to support two different technologies such as 4G and 5G in the same band. 5G standalone instead is an architecture, is a network architecture that is something that is going to be deployed starting essentially for this year. Let's say that the DSS can live with both architectures, so NSA, NSA. I would say that the two things are somehow not completely related between each other.
Okay, thanks. Next question: what is the 4G lifetime? Should we expect 4G to phase out quickly?
Well, that's a good question, and the point is that if we look at the number of devices that have been, in general, not only IoT, I refer to also at this point also the consumer devices such as a smartphone and so on. The quantity of devices deployed everywhere in the world is so high that of course network operator cannot afford to phase out 4G so quickly. In addition, because the deployment of 5G that started with the NSA implementation, so no standalone implementation, and where there is the need of 4G as main technology, at least for the signaling part, of course we expect that the 4G will last for still many years. In addition, we have not to forget that there is a large installment base of IoT devices that has been deployed in the field, and therefore if we decided to phase out 4G would be really a challenging situation, because all those devices should be upgraded to 5G in order to be back again, let's say, working. So at the end, we expect that the 4G will last at least till the end of this decade, and then will gradually, let's say, phase out in the next decade.
Great. Next question here: are the Telit Cinterion 5G products capable of working on DSS deployments?
Yes, definitely yes, because otherwise customer would not have the possibility to let's say to develop 5G applications using the current product, and also in particular the 5G implementation of the network operators.
Great, thanks, Marco. I believe that is all the time that we have got for today. Audience, please be sure to check your inboxes in the coming days. We will send out that replay link. Marco, thank you so much for your time today, and thank you to everybody who joined us.
Thank you, Amanda.